Algebra 1, Lesson 53, the power rule for exponents and conversions of volume. Now, the power rule for exponents is actually really simple and really awesome. We just have to get some main concepts down and make sure we understand them. So we know that multiplication is a faster form of addition, right? And we know that exponents are a faster form of multiplication. Now, what happens when we want to multiply numbers with the same base times each other? For example, if I have p to the power of 4 times p to the power of 6. Well, the power rule tells us that, well, this is how the book states it. They tell us that if m and n are real numbers and x is not equal to 0, then x to the power of m times n equals x to the m times n. That's a really mathematical way of saying what I'm about to show you right now, which is this. If we remember that exponents are a faster form of multiplication, then that means p to the power of 4 is actually saying p times p times p times p. 4 p's, right? So we agree that this is equal to that. So if we were to take this and then multiply it by p to the power of 6, which can be rewritten as p times p times p times p times p times p, right? P multiplied 6 times, we can figure out the answer to this problem. So all we have to do now, if these are being multiplied, is we just count up all the p's, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we can say that that is equal to p to the power of 10, right? Because we have 10 p's being multiplied. So that's pretty much the power rule in a nutshell. And what it tells us is that when we're multiplying variables with exponents that have the same base number, in this case p, all we have to do to multiply them is add the exponents. So what the power rule says that instead of drawing all this out every time, all you do is you take the exponents and you add them. So I could take 4 plus 6, that equals 10, so my answer will be p to the power of 10. Another way to think of it is to put a noun onto the unknown. So I could say this, instead of saying p to the power of 4, I could say I have 4 pizzas. I have 4 pizzas and 6 pizzas. How many pizzas do I have in total? No, it's 10 pizzas, right? Or pizzas to the power of 10. Let's see here. Let me find an example from your book. Oh, and this also works with parentheses as well. So if we had something like x to the power of 5 in parentheses, then outside of the parentheses we had a 3. This expands the power rule even more. So what this 3 outside of this parentheses is saying is that we actually have 3 sets of these parentheses. So this is equal to x times 5 times x times 5 times x times 5, right? Now, this is a little bit different because using this logic, you'd want to add it and say that's x to the 8. However, if you remember what power is actually saying, it's saying we've got 3 of these things. So when we think of it this way, instead of doing x to the 8 as our answer, which would be wrong, we think of it this way and we realize we've actually got 5, 10, we've got 15 x's. That's going to equal x to the power of 15. Now the faster way to do this, if you use the power rule, is when you have an exponent outside of the parentheses, you use distributive property. You multiply. 3 times 5 would give me x to the power of 15. So when it comes to exponents, if there are no parentheses involved, we're going to add the exponents to get our answer, right? Because it's very straightforward. We're just counting the number of p's there are. However, if there is an exponent outside of a set of parentheses, we're saying we have 3 groups of 5 as opposed to 3 plus 5. So we would then multiply. All right, so that's the power rule in a nutshell. Now what if we threw negatives into the mix? Like let's say we had x to the power of 3 in parentheses, and then outside we had negative 2. Well, the same multiplication rule would apply. We would just take negative 2 times 3, which gives us negative 6. So this is going to equal x to the power of negative 6. And that's our answer there. All right? So the power rule is pretty simple. It's just something that is easily confused because we've been learning a lot of rules about exponents and polynomials. So do not be confused. Every time you have an exponent inside parentheses, you multiply. If there are no parentheses, we add. Now, that takes us to, oh, sorry, I've got one more example for you, because the book never gives you problems as easy as in the examples. So let's say we have a problem like this. We have 3 to the power of 0, y to the power of -2, z to the power of 5, in parentheses, and then outside, oh wait, sorry, there's also a denominator, x to the power of 3, all in parentheses, and then outside of the parentheses, we have an exponent of -3. I just realized I wrote all of that off camera. So this is the problem that we're dealing with. This is stuff you'll see on your homework. So what the power rule tells us is we take this -3 and we're going to distribute it, not to just one of the exponents, but to all of the exponents. So we'll go ahead and take this -3. -3 times 0 is still going to be 0. So we still have 3 to the power of 0. -3 times -2 gives me a positive 6, so I have y to the power of 6. -3 times 5 gives me z to the power of -15. And then in the denominator, x3 times -3 gives me x to the power of -9. Now, let's say we had to write all of these variables in the numerator, and then we also have to finish simplifying, because we can't just leave 3 to the 0. That's not true. 3 to the 0 is actually equal to 1, so I can go ahead and cancel that out and just write it as a 1. Now, if I wanted to write all of these with the exponents positive, I would have to take this x, move it to the top, and the z, move it to the bottom, which means my final answer will be x to the power of 9, y to the power of 6, over z to the power of 15. So, using the power rule, even if you have more than one variable inside the parentheses, you distribute to every single one, numerator and denominator alike. All right, last thing is conversions of volumes, and these aren't too hard. We're just going to keep using our unit multipliers and follow those rules. So let's say we had to convert 180 feet cubed to inches cubed. Sorry. So we have to convert these feet cubed to inches cubed. Well, we're going to follow our rules of unit multipliers. We take our starting number, we put it over 1, and then we put our word there, and don't forget to put the cubed. And then we're going to start with a unit multiplier. Now, if feet is on the top, then feet will go on the bottom. We're going from feet to inches. We know that there's 1 foot and 12 inches, so we finish filling in that unit multiplier. Now we're going to cancel. I will cancel this feet, and I actually have feet cubed up here. So think of it this way. If I had x cubed over x, that would just cancel to x squared, and that's what happens here. So this 3 becomes a 2. And what we'll notice is with volume and like with our areas, we're not done. We have to keep going. So when you're converting volume or cubed units, you're going to have to use all of your unit multipliers 3 times in order to completely get rid of that exponent. So this second feet will cancel out that squared, and this last foot will cancel out the last foot. And from here, I can go ahead and start copying my answer. So I've got 180 times 12 times 12 times 12, and then I've got inches times inches, which is inches squared, times inches gives me inches cubed. And that's my answer. So when you're converting volume forms, make sure you multiply your unit multiplier 3 times every single time. And if you want, so since we're going to be getting lots of large numbers, if you want to simplify your answer a little bit faster, another way to write it is I could have written 180 times 12 cubed inches cubed. And that's an acceptable form of the answer as well. All right, if you have any questions, let me know on Moodle, and I will see you in class.